Hello students. So in the last class we ended up with the expression for magnetic dipole moment expressed in terms of angular momentum for a revolving electron in the hydrogen atom, right? The expression that we took or derived is mu L, which is the magnetic dipole moment is equal to E by 2m E, where me is the mass of electron, E is the charge of electron times L, right? Yeah, I think I wrote it as E by m into L by 2, right? That's also fine. This is the other way of expressing the same expression. I just took 2 inside the bracket. So it's E by 2me into L, which is the expression for magnetic dipole moment expressed in terms of angular momentum. Okay, but this expression gives us the idea about magnitude of magnetic dipole moment. Okay, only about the magnitude. If we express the same expression vectorially for a revolving electron, okay, finally electron is a revolving body, isn't it? So it doesn't matter what kind of charge does the body possess to get the direction of angular momentum, isn't it? It's always right hand thumb rule which will give us the direction of angular momentum. R cross F sorry, R cross V will give us the direction of L, right? But when it comes to magnetic moment, there the direction matters, because current direction is decided by the direction of flow of positive charge. Here the direction of here the particle which is revolving in the hydrogen atom is negatively charged, and hence the current would be exactly in the opposite direction, isn't it? So when I express the same expression of magnetic dipole moment in terms of angular momentum, I need to introduce a negative sign when I express it in vector form. Okay, so expressing the same expression vectorially, I should now write vector magnetic dipole moment is equal to E by 2 me, everything remains the same, into vector L, but this time now I need to introduce a negative sign. What is the significance of this negative sign? The significance of negative sign is the particle revolving around the nucleus, the electron. That's what we are studying now, right? The motion of electron. The negative sign signifies that the revolving particle, the electron is negatively charged. That is why we need to introduce this particular negative sign. Okay? And at the same time, we can also get the idea about the directions of mu L and L, isn't it? So this negative sign also signifies that the direction of L is exactly opposite to that of direction of mu L, or in other words, direction of mu L, direction of magnetic dipole moment for a revolving electron, particularly for a revolving electron, is exactly opposite to the direction of angular momentum. Clear? So let me give you the clarity. Say this is the revolving electron. Let me assume that the electron is revolving in a clockwise direction like this. Okay, then what is the direction of angular momentum? L. See, L is given by R cross F, right? Okay, I'll take the R cross F approach itself. So this is R, okay, this is R. L is given by R cross V, right? It's actually R cross P, angular linear momentum, but P will have the same direction of V. So I can take R cross V to get the direction of omega and hence the direction of L. Okay, R cross V will give us the direction of L. So now this is R, right? This is V. What is R cross V? Okay, R. Okay, observe carefully. This is R radius. If I extend it, the direction would be like this. But the direction of velocity at this point is like this, because the particle is revolving in clockwise direction. So it is R cross V, which means the direction of angular momentum, for this electron in its orbit is into the board, right? Cross into the board, right? R cross V, R cross V is into the board, represented by cross. So this is for angular momentum. So what is expected here? What is the direction of magnetic dipole moment? So if angular momentum is into the board, magnetic dipole moment should be out of the board, isn't it? It should be coming out of the board, which will give us the direction of magnetic dipole moment for the revolving electron. So that's it. The basic significance is direction of mu L and L are exactly opposite to each other. Okay. And now, using the same expression, we are going to define a new term here. Okay. The term is gyromagnetic ratio. Gyromagnetic ratio. Okay. So this gyro term, gyration or gyro term is somewhat related to the rotational or revolutionary rotational motion, or the motion of a body under revolution. Gyro part. The magnetic part is somewhat related to magnetic dipole moment. So you might be thinking that this term, what we have chosen, is a ratio of two terms. Which are those? Which are available here? The ratio of magnetic dipole moment of an electron in the hydrogen orbit, in the hydrogen atom, to the angular momentum of the same electron in its orbit is called gyromagnetic ratio. What is the value of gyromagnetic ratio? So according to the definition, the ratio of mu L to the L, okay, the ratio of magnetic dipole moment to the angular momentum, the ratio of magnetic dipole moment to the angular momentum of a revolving electron in its orbit is called gyromagnetic ratio. Okay, this term is gyromagnetic ratio. Now, what is the value of gyromagnetic ratio? Equal to mu L by L is equal to E by 2me. See, this gyromagnetic ratio is a constant term, right? Look at this. E is a constant, mass, charge of electron. Me is constant, mass of electron. 2 is a number. So E by 2me, this whole term is a constant. So gyromagnetic ratio is a constant term. Okay, you can obtain the value of that, but it is defined using mu L and L. It is the ratio of magnetic dipole moment of a ratio of magnetic dipole moment to the angular momentum of an electron revolving in its orbit of hydrogen orbit. Okay, so that is what is gyromagnetic ratio. And now we shall move ahead to see more to connect these things with the modern physics. Which means, yeah, we need to discuss those things. We will discuss those things in the coming chapters when we come to the chapter of atoms, nuclei and all. Particularly in the chapter of atoms, we will discuss the different models of atom given by different scientists. Out of all those models, one model is important for us, Bohr's model, which will give us many interpretations and postulates which will help us in understanding the structure of atom in detailedly. So we are going to consider one of that principle or postulate given by Bohr here. Okay, see, what are the different models of an atom? So many scientists try to interpret the structure of atoms. Even today, we do not have a microscope which can look inside the atom. Okay, it's all theoretical basis and then some practical results which can prove this model. That's how the model is been developed. So in previous days, so many scientists came up with their own theories, with their own practical support for those theories. Many of the theories vanished, and many of the theories came in between, gave very good support for many practical phenomena that were happening, but they were not complete. They could not give the complete picture of the atom. One of that kind of model is given by Bohr. Bohr's model could explain many things happening in the atom or due to the atom, many things related to atom, but it could not explain give the complete picture of atom again, but it was useful. And we now will be considering one of the postulate of Bohr here directly, and deriving the expression for an important term which is called Bohr's Magneton. Okay, Bohr's Magneton. Let us do it now. Okay, the expression that we have obtained is mu L is equal to mu L is equal to E by 2 me into L. We will be bothered more about the magnitude part, don't need to worry about the rest, the vectors and all, nothing to worry. Okay, it's more about magnitude part of that. So mu L is equal to E by 2 me into L is the expression that we have obtained, and we have also defined Gyromagnetic ratio using the same expression. And now we are going to apply Bohr's postulate, one of the Bohr's postulate into this expression, because one of the postulate given by Bohr is related to the angular momentum of the revolving electron in its orbit. And the expression is, according to Bohr's postulate, the angular momentum is equal to integral multiple of a constant. Okay, integral multiple of a constant. That constant is h by 2 pi. Don't need to worry about the inner meaning and detailed discussion of Bohr's postulate. We will discuss them in the coming chapter, but for now we will take the direct expression of L. Okay, so according to Bohr's postulate, L is equal to nh by 2 pi. Okay, this is a very beautiful expression actually. It has its own inner meaning, and that is where the quantum physics starts with. It's quantized is what we say. Okay, but we'll discuss those things in the coming chapter, atoms. But here I'll directly take the expression of L according from Bohr's postulate. Okay, so it's according to Bohr's postulate. So L is equal to nh by 2 pi. If I substitute that into this expression, which we have already derived, mu L becomes equal to E by 2 me into nh by 2 pi. So now what is this n? N is any integer that we can choose. Okay, n can be equal to 1, 2, 3, 4 and so on. That is why we say the integral multiple of n. So what value should we take now? We will take n is equal to 1, okay, for getting the expression of mu L, which will then be called Bohr Magneton. Okay, if I substitute n is equal to 1 for this particular expression, that itself becomes Bohr Magneton. Okay, so basically what is n? N is the orbital number, okay, the orbit in which the electron is revolving. So now we are concentrating on the first orbit. So mu L becomes equal to simply E by 2 me into h by 2 pi. Okay, why? Because for Bohr Magneton, n is equal to 1. Okay. Yeah, you might ask what is h? H is a constant again, nothing to worry, it is not a variable, it is a fixed constant just like E and M. Okay, it's called Planck's constant. So now the expression for mu L put all together becomes equal to EH by 4 pi me. EH by 4 pi me. This itself is the final expression for Bohr Magneton. Okay, this value itself is called Bohr Magneton. See, if I am naming a value as something like Bohr Magneton or any constant, so all the terms in it in the defined term in the defined quantity should be a constant. So when I say Bohr Magneton, the value of Bohr Magneton is fixed, it's a constant, because now if you see here, all the terms in the RHS what we see are all constants. It's a combination of constants, nothing else. E is a constant, H is a constant, Me is a constant, Pi is a constant, 4 is a number, it's also a constant. It's a combination of constants together giving the value of certain other constant, and this value is called Bohr Magneton. Okay, so Bohr Magneton is particularly taken for the first orbit n is equal to 1, and hence this is the final expression for Bohr Magneton, which is EH by 4 pi ME. Okay. Yeah. Now it's a task for you. Take the value of E, H, and ME, and get the value of mu L. Okay, it's a constant. It's just simplification. Do it properly, you get the value of mu L. So mu L is the Bohr Magneton, which is a constant value which can be taken after simplifying E, H, and Me. So now how to define mu L? What is mu L actually? Mu L is magnetic dipole moment. For what? For a revolving electron. In which atom? In hydrogen atom. Now in an hydrogen atom there can be any number, the orbital number can be anything. If you give certain energy to the electron, it will go to the higher energies, the next orbit. But if the electron here, particularly we have chosen n is equal to 1 for Bohr Magneton. So if I want to define Bohr Magneton, okay, it is quite simple. Bohr Magneton is the magnetic dipole moment of a revolving electron in the first orbit of hydrogen atom, isn't it? First orbit makes sense when I take n is equal to 1. Okay, for the in the first orbit of hydrogen atom. This hydrogen atom is the basic consideration that we took, right? So this is the definition of Bohr Magneton, isn't it? Easy. So Bohr Magneton is nothing but the magnetic dipole moment of a revolving electron in the first orbit of hydrogen atom. Okay, that's definition is important, and this derivation is also important. Very easy derivation. This is the first basic formula that we already know, and this is the new term that we are introducing here, L is equal to NH by 2 pi. We'll put that here and take the consideration of n is equal to 1 for Bohr Magneton. That's it, nothing else. Okay, so this is a derivation with the definition. Okay, the next topic that I am going to take tomorrow is moving coil galvanometer, which is very important topic and interesting one again. But again, if I start it today, it takes more time in the same session, and also I want you to show the actual galvanometer and explain the construction and working simultaneously. So let us take the topic tomorrow. But it's again, it works on the basic principle that a current carrying coil kept in the external magnetic field experiences a torque, isn't it? We have discussed about it. The amount of torque expression is also derived. Tau is equal to NIAB, isn't it? NIAB sin theta, the complete expression. So now based on the same principle, see, this is the basic mechanism, basic principle which we had, right? You keep a current carrying conductor in the external magnetic field, it will experience certain torque. Now that's the basic principle. Now it's our ability, our imagination to use that basic phenomena in various other fields and applications. So one of the device that we can design using that principle is moving coil galvanometer. Because if I make certain current flow through this device, then see, obviously here we can see that torque experienced by the body is directly proportional to the current. More the current, more the torque. So that we can design an instrument which can show certain deflection according to the amount of current flowing through that. More the current, more the deflection. Lesser the current, lesser the deflection. So we can make use of this property to make a measuring device of current. isn't it? Not only current, we'll also do it for voltage, and we'll discuss the construction working of moving coil galvanometer with the actual galvanometer in the next class. Thank you.